Okay, let's start with the review. The way we're gonna do this review is that you have questions? No questions? All right, so you want it?
Really?
Really? If there's no question, what I'm gonna do? Everyone knows everything.
Well, can you give us a rundown of?
I need a specific question. Not, can you tell me about the round? No. This question or that? Yes.
Can we go over some scheduling problems?
What specifically what? I'm not going to do the review of all the scheduling here today for people who just come to the review. I just need the specific questions.
Can we go through the common mistakes we always do on the previous test?
Pardon me?
Can you go through the common mistakes that everybody does on this kind of problems?
In the previous test?
From previous class, I mean.
Oh, so it was a year ago or so.
Just go through the common mistakes.
Well, no mistake. There was a very interesting question with the scheduling algorithm for round robin in this class this year. That we have this problem. We have this problem, and there are two different ways to answer this problem. Let's say we have P1, P2, P3, and P4, and then we have arrival time 0, 2, 4, 6. All right? And then we have 6, 3, 8, 5. Okay. In this problem, there were two types of answers, right? So what I would like you to do is to solve it now. Tell me what is your answer, and we'll discuss the problem. Okay? I'll give you a couple of minutes.
Is it a 5-second quantum? 5 millisecond?
Pardon me?
Is it a 5-second millisecond quantum?
5 minutes. Don't worry.
No. We're doing.
This is for round robin. First
Round robin. Okay. Average wait time is what we do in scheduling. When we have preemptive scan, yes or no? Preemptive scan, yes or no? Huh? Yes or no? Preemptive scan, yes or no? No, scan. You. Who have preemptive scan? Or round robin? Okay, you must start studying all the scheduling algorithms for this scheduling and for CPU scheduling. So the scan is for this and preemptive and non-preemptive for this. So absolutely, I mean, can we have preemptive scan? Preemptive is to take the CPU by force. So we cannot have any of the CPU of this scheduling algorithm with preemptive or non-preemptive. Okay? If you are in the middle of an I/O operation, know the problem is going to take and take this under by force and put the other one out. You have to wait until the I/O operation ends. Okay? So that is impossible. There's one question there. Yes? Okay.
What's the quantum for this one?
Round robin? 1, 0, was 5?
Yeah. 5 seconds.
Okay.
5 seconds.
Okay.
Round robin? Yeah.
Usually, in an operating system book, you find this problem. In general, they don't have this. And you're going to see why. Because people have the tendency to answer this problem this way. So P1 arrives at 0. P2 arrives at, let's say, 2. 3 at 4. And P4 at 6. Correct? Okay. So when P5 has run for 5 time units, only 1 unit is left, right? Do you agree? Okay, at that moment, we have 2 and 3 in Q, which means that the way they arrive is,
Oh, yeah.
the way they arrive is P1 first, right? And then P1 gets the CPU, which means it's not in the ready state. Remember that the Q represents the ready state. Then, while P1 is running, P2 arrives, and then P3. And still, P1 is running. And then, at time 5, there is a timer interrupt, correct? P1 goes back here. And then, who takes the CPU? P2. P2 is going to run for 3 time units. What type of interrupt are we going to have there? Pardon? End of program, right? So we have an end of program. So it occurs at time 8, right? And then it means, well, at that point, it means that P2 is in the CPU, right? And that is what we have. Well, P2 is running, correct? When there is an end of program, P2 gets out of the system. But while P2 is running, P4 arrives. Right? So who takes the CPU now? P3. This one went to 0. So P3 gets the CPU. So P3 is here. Run for 5 time units. Who takes the CPU now? P1. Okay?
Are we just showing the leftovers? Because that would be a 3 left over on P3.
after. Yeah.
This one? Yes.
Yeah, it would be.
You're right. It should be a thread. Okay. So who is the next to get the CPU? When P3 goes back, where goes P3 back, right? The first one in the queue is P1. Okay? And that's why I would say perhaps all or most of OS books, when they talk about round robin, they only give you the time and the process name, let's say. So you can go 1, 2, 3, 4, 1, 2, 3, 4, 1, because it's the natural way to implement the algorithm. But if you're having arrival times, then you have to take them into account, because in round robin a process gets a CPU, and if the process doesn't run to completion, has to go back. Okay? So we have many answers in the homework where people did P1, P2, P3, P4, P1, and other people did P1, P2, P3, P1, and then P4. And practically we accepted power.
Is there a new homework that we need to have done, like number 4? Is that already due? It was due on the 21st?
Yep. 4 is already. We're done with 4. I think it was due that. Yes.
Monday.
Already graded. Yeah. When do I have homework after the next week? About memory. Next one. Okay. So this is something that you have to take into account. I mean, if the question doesn't have arrival time, you just do the round robin as usual, right? One after the other. If the question has arrival times, then you have to, let's say, take into account the arrival time. Okay. For instance, if this question has that the arrival times are 3 and 5, you can take them into account as well. But at that moment, let's say that
If P4 comes in, yeah, there's gonna, like, which one gets it, P1 or P4 at 5, because P1 is finishing it at moment 5, and it'll be thrown back into the queue.
right. At that
5
point,
goes to the runner. Which
here,
one would
okay,
be?
here, let's say this one is if P4 is arriving here, it means that there is an end of program on the one side, and the other one is that P4 is arriving. No, it's not end of program, goes back. So we have the problem now. That we have P1 running, P2 arrives, P3 arrives, and now when P1 comes in, P4 is coming at the same time. Okay?
Yeah.
If you have a question like that, then, and it doesn't say who had, if it says, the question says, the priority to get the queue is always the new one, or the one coming from the CPU, because we assume that they are occurring simultaneously, you should have a note. But if you don't have it, you have to say, I will assume that the priority is for process entering for the first time, or I will assume that the process is in the CPU. Okay? In those cases. So you can see that in this type of algorithm, if we're taking into account arrival time, it gets more complicated, right? Now, if you have something like this, there is arrival time, and you can take the arrival time, but in this case, not having arrival time will give you the same result, because process 1 arrives and takes the CPU, and when process 1 is running, all the processes arrive, which means in this example, you have P1 here, P2, P3, and P4. So in this case, P4 will get here before P1 finish the quantum. Is that clear? Is that clear for everyone? I'm trying to clarify that question round robin because it's tricky. So you can take into account the quantum, and however, in this one it works 1, 2, 3. That one will be 1, 1, 2, 3, 4, 1, 2, 3, 4, because all of them arrive before P1 finish the quantum. But take that into account, okay? Is that clear for everyone? Yes? Okay. Any other question that was confusing in the homeworks? Yes?
So this one ends at P4 and at time 19.
Which one?
The original problem, does it end at P4 and at time 19?
The original problem, we have
Ends at 21.
P1 here, one time unit, it's 14 I guess. And then the next one to get the CPU will be P3.
Or T4.
Yeah,
Or
it's
P4.
P4.
P4 for 5 time units, right?
Yeah.
So 19.
Yep.
And then P3
22.
for equal to 22. Okay? And this is important because that will change the waiting time of one of the processes. Is that clear? Okay. Where else do you have doubts? Any other question?
Do we need to study any definitions? Like, what definitions from what chapters do we need?
The last homework was pretty
Most
much
of the
definitions.
problem, most of the exam will be problem on this scheduling and CPU scheduling. There are concepts which are not definition, but you have to apply. For instance, what does it mean that the quantum is too big in a round robin algorithm?
It will be.
How they are? Yes.
It takes too long to process.
No.
Behaves like first.
Anyone?
Behaves like first come, first serve.
Behave like first come, first serve. Okay? These are the kind of questions. It's not the final concept, but that you need to know how to apply it. Okay? What else?
When the quantum is too small, that's the overhang is too big.
Pardon?
When the quantum is too small, that's the situation where it's too big and not enough, right?
Right. Because what we're saying there, imagine that we have P1 here, and then this is, how do we call the time in between one process and the other? Context switching, right? Let's suppose this is P2. This is P3. So we're saying that the time to switch from one process to another, context switching, is much larger than the time it takes to run in the CPU. So there is too much overhead, and the processes are running very little. So that's what is happening. Okay. What else?
What I/O operations stuff do we need to know for the test?
What I/O operation?
Yeah, like what about I/O operations? You said most of the test was going to be CPU scheduling and process scheduling, but what I/O operations things do we need to
I/O operation, you mean like read, write, close,
well, no,
open?
The stuff about the I/O request queue and I/O request block device. and whatever.
Okay, you need to know everything about that.
Okay.
I mean, you need to know what is every time that a process initiates an I/O operation, there is an start I/O, right? And it moves to the state that it waits for I/O. And then that the OS for when the process requests services for I/O, the I/O operating system is going to create an I/O request block, and it's going to insert that I/O request block in the I/O request queue. Okay, and on the other hand, there will be a device handler taking the I/O request blocks and initiating I/O operation. I think Wednesday last week we explained all that producer-consumer approach, right? So we did it and explained it in detail. Any question about that?
The producer consumer is just pseudocode with
Pseudocode.
the mutex and mutual exclusion, correct?
You need to use the producer-consumer, and then the queue, the buffer is the queue.
Insert queue.
Insert I/O request block in queue,
Yeah.
get I/O request from queue. It's a standard producer-consumer. No. The only thing is that you need to have a good memory to remember everything. No, memory will be for mostly for the final, because we just keep the very beginning.
Could we maybe go over preemptive short stop first?
Okay. Okay, in this question here, we have some processes, right? P1, P2, P3, and so forth. And then, in question number 2, it says 2 and 3. One case is preemptive, and the other case is non-preemptive, right? So what does it mean? Preemptive means that if a process has a higher priority than the one that is running, it will take the CPU immediately, right? And non-preemptive means that you have to wait until the one that is using the CPU finishes run to completion, let's say, put it that way. Okay? So we can have an example, like, for instance, P1, P2, P3, P4, okay? And then we have 6, 3, 8, 5, all right? And then we have okay.
Are those the arrival times or those
Arrival time, CPU time, process name, shortest job first, preemptive. Yes.
Is
But
shortest
before
remaining
going
time
first.
first the same?
Pardon me?
Shortest remaining time first, is it the same as?
Okay. Let's go on that. Give it 3 minutes. Compute the average waiting time.
switch to 2.
All right, we are in preemptive scheduling. Let's see what happens here. Okay. Which one is the third process to arrive? We have P1 and P4, right? Both are in memory. Which one will take the CPU?
P4.
P4. Why? Because
The
the
shortest.
priority is the shortest time. So P4 take the CPU. But when P4 has run 3 time units, no 3, 2 time units,
Also, we had a
Switch?
well,
Because
P4
They're
has
both,
run,
they're both 3 at that point.
Yeah, they're both on equal footing.
okay, let me talk. Then when P4 have run for 2 time units, I have something new to tell you. We have 2 of them with time 3, right? Okay, this one and this one. So which one will take the CPU?
P4.
Why P2?
The arrival time.
Pardon me? Who said P2? Why?
shortest.
Both have 3.
The arrival time.
So right first.
What happened with the arrival time?
Yeah, P2 arrived at 2. So,
P4 arrival at 0.
right, so that comes in first and then after that comes
But we are going to give the processor to the one with the highest priority.
So say in P4 that it's already there. P2 is just in the queue. It's not used.
Okay, and you?
P4 finished before the
You pick P4 in the CPU? Okay, remember that when there is a tie, the OS is not going to take one out of the CPU and see that both have the same, let's say, priority. You can just give the priority to the one that is running, you don't have to do anything. Okay? So when there is a tie, leave the one in the CPU. Okay? So which means that P4 continues running. And P4 will run up to 5 time units, right? So P4 gets up to here. This is P4. Now, which one, what process will take the CPU?
P2.
P2 or P3?
P3 could also take it.
P2 because it arrived.
Oh, it's in the queue first.
Remember, in case that they are in the queue, you apply first come, first serve. Always you can apply first come, first serve because in the former problem, P4 came in before, right, P2. So when there is a tie, always apply first come, first serve. So in the first case, was P4 already in the CPU because P4 arrived first. Now we have 2 processes, 2 and 3, the same priority. There is a tie, first come, first serve. So P2 takes the CPU. Now it's P2 who takes the CPU. All right? It's going to run for 3 time units. And then P4,
P4 stuff.
and then
No, P3.
P3, right. P4 is out of the system. And then P1. Yes.
For example, on the test, do you want us to show the 2 and the 5? Or just 5 just because
In the test, you have to show all your work. Let me tell you what the reason is. If you don't give me the Gantt chart, let's say if you give me this P4 without this division here, if you give me P4, P2, P3, P1, right? If you give me that, I'm doing this just to take the decision. But if you just give me P4, that's okay. But you have to give me the Gantt chart. You have to give me all the calculation. I mean, you cannot tell me average waiting time 20. If you have only that as your answer, even if it is right, you get 0. Yes?
Hypothetical problem. If P3, the time to finish it was actually 2 seconds instead. So P2 P2 loads first in the queue, and then P3 loads, but it's actually a shorter time. Would P3 switch places from P2 in the queue?
Let's see. Let me finish with this explanation, okay? So, in this case, as I was saying, you don't need to write this here. If you put it there, it's better because you understand what is happening. But if you just write P4, it's fine, okay? Is that clear for everyone? Okay. So your problem is that to change this one by 2?
Change P3, the time takes complete to 2 instead of
2?
3. Or no, not arrival time, arrival time is 4, but the time it takes to complete is 2.
2. Okay. What is going to happen? P4 gets a CPU, right? And it runs, this time, there is no problem. It's going to run here, right? At that point, we have these two processes. So P3 is going to take the CPU in that case, because P4 is going to run for 4 time units, because when this one arrives, it has 3. We're going to keep 4 in there, and then when the next time, when this one arrives, P3, P4 has 1 unit left. Okay? And in case that these ones arrive in 3, then what is going to happen is that they have the same time, the same remaining time, so there is a tie. P4 remains. But if we have perhaps 2 and 3, things are going to change. Because P4 gets the CPU after time unit, after 2 time units, this one has 3, right? So this one is going to take the CPU. Yes?
So then when would P4 come back in?
Pardon me?
When would P4 get the CPU?
Depends on the priority. Because let's suppose, let's try to do this one.
Be right after.
Okay, who's going to take the CPU first? P4, right?
Yep.
And so P4 is running at time 2. Time 2, there is a process that arrives, which is P3. All right? P3 has 2 time units. This one has 3 left. So P3 takes the CPU. Excuse me. For 2 time units. While this one is running, this one is in. Okay? This has 3 and this has 3. Which one is going to take the CPU?
P4.
P4, because when P4 went back into the queue, P2 was not in the system. So P2 arrived later. Okay? Is that clear? So we're going to have then, who's going to take the CPU? P4, then P2, then P1. Excuse me.
And they'll run all the way through to the end, right? Because once they're all in the queue, they just run first come, first served, right? Like for the next,
That'd be,
Which one?
That'd be
like
non-preemptive.
for the next after P4, it'll be 7, correct?
P4 is 3.
Yeah, there's no arrival time, but it just finishes through the end each process.
Well, here they're going to finish it to the end because the time they have. This one has 3, the other one is 3 greater than 6, and so forth.
Yeah, exactly.
In this example, yes. But if there is another process, let's say if another process arrives with more time, it will take it. Okay. So this is the kind of analysis you have to do. The main 2 problems are round robin with arrival times, or preemption or not, and not preemption here. For non-preemption, well, it's just the one that is running runs to completion, and then you take the decision. Okay? Which means with if we are running this one with non-preemption, before take the CPU, and it's going to run for 5 time units. At that time, you have 2, 3, and 6. You're going to do 2, 3. You're going to do 3, 2, and 1. Okay? So the process to get the CPU, you allow that process to run until the end, and at that point you check the CPU time for each one of them. The one with the smallest CPU time gets a CPU. Okay, these are the kind of problems that you can have with CPU scheduling. If that is understood, I don't think you're going to have any problem in the exam. Okay? What else?
We're also doing disk scheduling.
Pardon me?
Three spans.
3 scan?
Yeah. Are the ones we did last week?
Like
Well,
a N scan or?
It's not 3 scan, it's N scan.
Yes.
Let's suppose we're here. A scan is an algorithm that we need to know in what direction the read-write head is moving. And it depends on the previous one. So when we say that this one is at 750, and the previous was in 17, we are moving that way. If we say that the previous was at 98, we're moving this way. So that's the only reason we have to give you the previous one. Okay? Now, a scan works this way. No. What is first come first served is the queue, but a scan gives service different. For instance, if in the queue, if we have in the queue, let's say 20, 58, 17, we're going to give service to 20, to 17, but not to 58, so it's not first in, first out. Because 58 is behind. So we have to go in this direction. We get up to 0, and then we move to 58. All right? So we just give service to all the requests that we have in the queue that are in the direction that we're moving onwards. Okay. The scan are very, all the variants, what we need to know is that it's a scan. So it means that if it is a C scan, we move in one direction, let's say this one, we jump here, okay, move again, up to the end, back here, and so forth. Okay, that's C scan. And the jump has a value. What is the value we are using in class for the jump? 5. So that's the value we are going to use. If you don't remember it, the exam says the jump, for me, the jump is equal to 3 or 10, whatever you like. All right? Because we need that for the calculations. Okay. Then, so we have scan, we have C scan, circular scan. Which means it's scanning just one direction. Yes?
For the jump, you just add the 5 to the total, right?
Right. So, circular scan. Then there is one which is called N scan. N scan is similar to scan, but you only take N requests from the queue, the first N request in the queue. If we do 3 scan or 4 scan, what it means is that if we have a request queue with 58, 70, 14, 100, 200, 18. So if we do 3 scan, we take 3 and apply a scan to 3 only. And then the next 3. If we do 4 scan, it's just to do group of 4. So you apply a scan with the 4 first request or the 3 first requests. Okay? And it's just a scan moving in one direction. Give service to those 4, And when you give service to the last request, you continue moving in the same direction and get the next group of 3 or 4. Is that clear?
Which one is the one used today's day?
Pardon me?
Or which one is the one being used the most? Or
The most one is a scan.
the scan the first one?
Scan. In real operating system,
Yeah.
scan.
And scan moves the same way as a regular scan, not a circular or C-scan?
No, like a scan. But just take n requests. If the queue has 100 requests, let's suppose that n is equal 5. Take group of 5. The first 5, the next 5, the next 5, and so on. Yes?
The same thing happening within the group, like the one that you have here, 58, 77 to 14. It'll be jumping like first come first
It
serve.
doesn't matter, because what is going to happen, it goes into one direction. Let's suppose we're moving in that direction. We give service, it's running 50. We're not going to give service to anyone, 14 only. And then when we're back, assuming before a scan, we're going to give service to 58, 70, and 100. In this example, if we are moving in this direction, there is nothing between, not only 14, so we give service to 14. And then we switch back, and in our way back, we give service to 58, 70, and 100. Okay?
When using a 3-scan, 4-scan, or whatever, are those 3, 4 numbers sorted, or are they just first come, first serve in those?
No, the queue is coming
Queue.
first in, first out, and we're taking group of 4.
You're just taking a group? Okay.
Then, when you take the group of 4, then you do them not in first in, first out, but you are selecting the one that in front of the read-write head.
Okay.
Which means you take just the first 4 in the queue, and then you apply a scan. But scan is not first in, first out.
Scan is, yeah.
Scan is just moving, and anything that is found in front,
Yeah.
give service.
So what's the purpose of 3, 4 scan then? Why wouldn't we just scan?
The problem with 3, 4, or 3 or 4 within a scan is that you're going to move back and forth, back and forth. In real life, what we have is a scan, because the I/O request blocks are arriving all the time, and the device handler is just taking one and giving service, taking another, giving service, and so forth. What else? Yes?
For any scan, we go all the way to the end, correct?
For any scan algorithm, N-scan, C-scan, or scan, you have to go to the end. For instance, if it is C-scan and you're moving from the outermost track to the innermost track, you go through the innermost track, jump back to the outermost track, and then from end to end. If it is N-scan, N-scan is a scan, but you just take N requests, give service to those N requests, and continue doing a scanning group of Ns. Group of 3, group of 4, group of 5.
There was one where it wouldn't touch that inner or outer limit. It would know which one was the last one in that direction. Head back. Which one was that? Was that C?
Look.
Look. Is that?
Look is similar to scan, but in a scan, look, we have to hurry because there is another class. In look, what it does is that if the last request is here, then you move up to the last request and turn back. And if the last request in the other direction is here, you go there. If it is here, you do it this way. Just to the last request in any direction. Last question here.
Anything from chapter 8 with like programs I/O withholding and interrupts?
Pardon me?
Anything from chapter 8 you just invoke my touch one. Like programs I/O withholding or interrupts?
If you see the slide, we talk about falling and all that, but I explained that to you understand the mechanism.